So once again, yes, thanks a lot for coming. First of all, I'd like to welcome you to this Artificial Intelligence for Renewable Energy Technologies workshop. I want to first of all thank a few people. Before we actually begin the workshop, first, I want to thank the AI Institute, which has provided us this opportunity to, also financially supported us to organize this workshop here.
All right. So thanks for the invitation to present today. I'm not Nas Meftahi, but she unfortunately couldn't present today, so she asked me to present her slides. I was involved with this work, so I should hopefully be able to go through the work that she's done. So this was a collaboration between RMIT and Monash University, and Dr. Adam Simriak was basically the main experimental person doing all this stuff under the supervision of Udo Bach at Monash. So basically, what Nas wanted to do was basically outline some concepts in machine learning and approaches with regards to materials, and discuss a proof of concept project that we did, and then finally like the full machine learning project. So there are different types of machine learning, and there's a lot more than what I'm showing here. But so Nas and I basically, we're computational chemists. So we're coming at things from a molecular background and then trying to apply that same logic and reasoning to materials and periodic systems. It can be quite different and quite challenging, like at least from our perspective. So in general, if you want to make a model for prediction, you need to have a very large and very chemically diverse data set, and you need to come up with molecular or chemical descriptors. The descriptors can be like functional groups, like does it have aromatics, does it have cations, anions, methyl groups, carbonyls, those kinds of things. Those can be the descriptors. And if you don't have a large and chemically diverse data set, or if you don't have good descriptors, you can actually end up with a very overfitted model, or just a model that's very poor at prediction. Now, in general, the approach is you take all of your data and you divide it and use 80% as the training set and 20% as the test set. So you take 80% of the data points and use that to train the models. And then once you have the model, you use that model on the remaining 20% of the data set to see, does it actually work? Does it actually predict the things in the test set that weren't used to train the model? Now, this is what we did a couple of years ago for organic photovoltaics. Basically, we had a bunch of organic donor molecules and organic acceptor molecules, and someone had actually done computation to get computed properties, photovoltaic properties, like PCEs, GSC, fill factor. What was the other one? Sorry, I'm not experimental, so I'm computational, so I don't do the Perovskite stuff myself. But basically, we built the models for these organic materials, and we were indeed able to predict. Our models were able to predict the photovoltaic properties of different donor and acceptor combinations. And then in principle, you can use that to build new organic molecules. You can just get the structures computationally and predict their photovoltaic performance without actually having to synthesize them in the lab. Now, the project that I'm focusing on today is actually a bit different because when we were asked to look at perovskite materials, this is something very different from what we've done before. And we did not divide the data set into a training set and test set. We actually used the entire data set as the training set to build the models. And instead of trying to build a model for prediction, we were trying to build a model for understanding the relationships between the properties of perovskite materials and their performance. So that's what I'm going to go through now. So this was the initial data set that came from Adam experimentally. So he basically has 16 device recipes. And then from those recipes, he made something like, what was it? So each recipe he did, he measured it 96 times. So Adam thought that he had a data set of 1,536 compounds. And I was like, well, this is really good, right? But then Nas looked at this data set and she's like, well, wait a minute. You just used 16 recipes and repeated those a bunch of times. So what has to go into the machine learning model is the information in the recipes. Like, what was the electrode? What temperature did you do it at? What were the additives? What was the composition? So those were the inputs. And so from those inputs, you do not have 1,536 input values. You have 16. So that's not a great data set for machine learning. It is theoretically possible to make a machine learning model from 16 data points, but it's not likely to be a great model. So Nas said, okay, so what else, what other information do you have? And Adam said, well, every time I make a device, we have a film thickness and a film spread. And I said, well, okay, well, since those can affect the outputted properties, we can actually use those as input values for the machine learning model. And then instead of, we don't have, because for each device that Adam made that has a unique film thickness and film spread, he measured each of those 6 times. So we don't have 1,500 data points. Now we have 256, which is not, that's still a somewhat small amount, but it's better than 16. And it's enough to attempt a machine learning model. So this is basically what Nas did. So these were the variables that Adam used experimentally. So he had 2 solution molarities, he had 2 possible electrodes, he had 4 different casting temperatures, 2 different possible additives, 5 different percentages of polymer additives added, and 3 different percentages of surfactants added. So those were the possible variables that can go into the recipe. So, excuse me, of those possible variables, that means there are 480 different possible recipes that can be made from these variables. And then in addition to that, we added the film thickness and the film spread to the model as other variables for machine learning to look at to see if we can find relationships between these input variables and the output device performance, the VOC and the PCE fill factor and the JCC. So when Nas made this model, she used what's called one-hot binary descriptors. So instead of using like polymer additive as a single variable, each percentage was a single variable, and the one-hot binary descriptors are, like it sounds, it's a binary 1 or 0. So if that variable is present in the recipe, there's a 1. If it's absent, it's a 0. And that way you can treat each individual component as a distinct variable. And the reason for that is, you'll see this in a second, is that when you get the output from the model, basically all it does is says if the contribution from that variable is positive or negative. So if you have polymer additive as a single variable, all it will say is the polymer additive is good or bad, but it won't tell you like if 3% is better than 4% or if 1% is better than 5%. But by treating each of these variables as a one-hot binary descriptor, you can see clearly which one contributes positively or negatively and to what extent they contribute to the final properties of these devices. And then finally, the film thickness and the film spread were added to the model as as continuous variables, because they could take basically any values, not just these discrete values. Sorry. All right. So these are what the results look like. And again, the reason for treating every variable as a one-hot binary descriptor is you can see individually which percentages are good and bad. So we can see that for the PVP, 1% and 2% have a positive effect. They have a positive contribution on the PCE, but 3, 4, and 5% have a negative contribution. So what this is telling us is like up to 2% of PVP, you have a positive effect. That's a good thing for your devices. But then you start adding 3, 4, 5%, it starts having a negative effect on the device. And by doing these as one hot binary descriptors, you can actually see which ones individually have the positive and negative effect. If you did it as a single continuous variable, it would just say PVP good or PVP bad. It wouldn't tell you which percentage was the good one or the bad one. So basically, NAS made a separate model for the PCE, the JSC, the VOC, and the fill factor. And then from there, basically looked at all these results and said, okay, so for each of these variables that you used when you were making these, we can predict which ones will give you the best possible device out of these combinations of parameters for your recipe. And so NAS said, okay, this is your champion recipe. Adam went back in the lab and made it. And this is what he got. And as you can see, like, compared to the 16 devices that he made initially, the champion recipe that NAS predicted actually does perform better than the other 16 devices that he made. Now, there's a couple of things to kind of mention at this point. One of them is that it's important to remember that machine learning doesn't always work. Like, you can't take any data set and expect that machine learning is going to make a great model. Like, sometimes the information that you have available to you in your data set is not enough for machine learning to learn the relationships between the input variables and the output properties. So sometimes machine learning doesn't work, and there's no way to know that beforehand. So the only way to know if it's possible is to try it. And so that's basically what we did here. By only making 16 devices, we wanted to see, is it even possible for machine learning to work? And what we showed is that yes, it was. The other problem with this this little test study was the way that Adam made these devices was the way you would approach the problem experimentally. So you make one device and maybe you just change one variable. Then you make another device and maybe you just change one variable. That's not a good data set for machine learning, because it doesn't cover the full compositional space very well. So we came back and we said, well, okay, well, let's do something different. So instead of you deciding what the recipes are, you just tell us which components you think might be good, and let us come up with the recipes. Because the fact is that, like, all humans are biased. You know, experimental people might have, we all have our own biases about what we think might make good devices. And those biases can actually cloud your judgment and potentially lead you in the wrong direction. So NASA are like, okay, well, we don't know anything about perovskites. So you let us make the recipes, and then we'll give you the recipes. You make them, and then we'll come back and do the prediction. So that's what happened. So Adam and Udo went and they said, okay, so what possible additives might make good devices? What possible temperatures might be good? What number of layers would be good for these quasi 2D Ruddleson-Popper perovskites? And so these were the variables they came up with. And they said, okay, so we give these variables to you, you come up with 100 recipes. And so we thought about it. Like, we thought about, you know, what methods should we use to make the recipes? And in the end, we just put them in a random number generator in Excel and made 100 completely randomly generated recipes. And then we gave those recipes to Adam. He went and made the devices, and then Adam measured the properties that come out of those devices, the PCE, JSC, VOC, and the fill factor. And then we took those results, we put them back into the machine learning, we built a model, and then just like we did before, we said, Adam, this is the combination of these variables that we predict will make the best device. All right. Oh yeah. And so basically what this gives us is, so with the combination of things, like gives us 16,000 possible recipes. So what the question we're asking is, if we make 100 randomly generated recipes, can we predict the best one out of 16,000 possible recipes? And basically, this is the results that we got from doing that study. And basically what you can see here is just looking at PCE, most of them were not good. So, I mean, this shows you, like, if you just make a bunch of recipes randomly, a lot of them are not going to be good, that's probably obvious. Like, this is where, like, if you're only going to make 100 devices and you're not going to do anything else, experimental intuition will win over just making recipes randomly. I mean, that should be very, straightforward and common sense. But the point wasn't to stop here. The point was to make 100 devices that then machine learning can learn the relationships between the recipes and these output properties. So basically, we took these 32 possible fabrication parameters. We put them into a machine learning algorithm that was developed at CSIRO. Basically looks at the 16,000 possible permutations and gives us a champion recipe. So basically, these are the statistics that came out. So out of the 32 parameters, you can see, look at the R squared, which is it's basically like the regression fit to a multiple linear regression, and the standard error of estimation basically is like on average for each data point, how far off is it from the real point. So getting an R squared of 0.5, it's not fantastic, but it's good enough to start to look at the relationships between the variables and the resulting properties. So in the interest of time, I'm not going to go through these one by one, but basically what these results tell us is for all the different input variables, which ones have a positive contribution and which ones have a negative contribution to the resulting property. So we did this for PCE, VOC, JSC, and fill factor. And basically, long story short, in the end, we predicted what we thought would be the best recipe out of these 16,000 possible combinations. So here we have the best recipe from the random model, randomly generated recipes. And then here is the recipe that we predicted would be the best one. So our champion recipe, Adam went back into the lab, he made the cell, he measured it, and yes, it is significantly better than the ones that were developed by random chance. And so basically that was a conclusion. So like the thing about this study is like, it's still like, even this part is still basically a proof of concept. We just want to see, like, is it possible to use this method to explore the photovoltaic properties of these 2D perovskite materials? Because the quasi 2D Rellston-Popper perovskite materials, a lot of them are found to be a lot more stable than some of the other perovskite materials that are currently being investigated. So even though the PCE was only about 16%, the stability of a lot of these devices was a lot better than a lot of what the other perovskites that people are looking at. And when I was talking to Udo about this, he said that some of these results that came out in the champion recipe actually were counterintuitive from an experimental perspective. Like, with all the knowledge that he has of these devices, this is not necessarily the recipe parameters that he would have chosen. So again, like, that shows you the value of the machine learning, is that you can get non-intuitive results. And finally, what Udo and Adam are doing right now is they're making a basically semi-automated to fully automated device manufacturing facility that will be able to make 2,000 perovskite material recipes per day. And so when you're making 2,000 devices per day, you really need to start finding new ways to analyze the data. And that's where machine learning can come in. So by making 100 devices, we were able to predict the properties of 16,000. If we're making 2,000 devices per day, we can potentially predict the properties of millions, billions, trillions of possible devices. And this is a massively more efficient way to explore the extremely vast compositional space of perovskite materials. So the value here is not using 100 devices and getting a PC of 16%. The value here is a methodology that can be used to explore millions, billions, or trillions of possible device recipes. So that's basically the conclusions. We used machine learning models to screen the possible permutations, and like to build these machine learning models, like it takes seconds to do the prediction. So like these are very, very quick and efficient ways of exploring the space. And the insights gained from seeing what compositions and what parameters have positive and negative contributions to the devices, that too can help guide which recipe parameters you're going to use in the next iteration. So yeah, there's a synergy between the robotic devices that they're building at Monash and the machine learning models that can guide how they should use their robotic devices. So that's pretty much it. I added some things for another project we worked on, but in the interest of time, I think I'll go ahead and skip this stuff. One thing I wanted to mention is that we've written an article on using machine learning to look at fluorescent polymers. And this is in the latest issue of Chemistry in Australia, which is available free online. So if anybody's interested, you can have a look. It's written at more of an introductory level. So if you're new to machine learning, it's worth having to read. It's only like 4 pages, and it might give you some ideas on how machine learning can be used. So yeah, Ness thanked me. That's nice. So we want to thank Salvi, NASA's supervisor, RMIT. We want to thank Syra Natrobe, Dave Winkler. Of course, we want to thank Udo and Adam, Excellence in Science, and ARC for funding. And thank you for your attention. And the last thing I want to say is, so this is me here at the bottom. I'm not really an expert in machine learning or AI. I thought I was. And if you're new to this, a lot of times you can learn how to use an algorithm and you can make models, but if you don't know what you're doing, your models might not be good. And I told Nas what I thought we should do, and she was like, "Nah, that's an idea, but that's not the best way to go about it." So if you're not a machine learning expert yourself, I strongly encourage you to collaborate with a machine learning expert, and it can really drive your research forward, and you'll learn a lot in the process, and maybe you will become an expert in AI. So thank you.